One of the main topics of this chapter are the 4 arrow pushing patterns, and we're going to briefly discuss them now. There are 4 patterns, and the first is Nucleophilic Attack. And we're going to abbreviate all of these patterns so that it's easier to discuss them with each other. The second one is Loss of Leaving Group. We'll abbreviate it LG. LG also stands for leaving group, so it can refer to the actual group that's leaving, the leaving group, or we can just use this abbreviation here to refer to the pattern, so that's LG. And the third one is Proton Transfer. Remember, to an organic chemist, a proton is simply a hydrogen ion, an H+ ion. So that would be what we're transferring, and I like to abbreviate it PT. And the last one is rearrangement. And I like to abbreviate RE. So let's take a look at the first one, nucleophilic attack. It's important that we begin to recognize these patterns because they will certainly take place in later chapters when we get into the nitty-gritty of organic reactions. And if we can recognize these now, it's going to make our lives a lot easier in the future. So let's just set up a reaction here. Got a cation, and we have the OH- anion, and it's going to produce something. So nucleophilic attack is where a nucleophile, and hopefully you recognize this as a nucleophile. It has several lone pairs. It has a negative charge. A nucleophile will attack an electrophile, and I like to abbreviate electrophile with E+. And of course, this is a good electrophile because it has the positive charge in the empty p orbital on the carbon. And so the nucleophilic attack arrow push looks like that. We want to be very specific with our arrows. We want to start at a lone pair. We want to end at the carbon or whatever atom we're attacking. And so the resulting structure, as you might have guessed, looks like this. And we've created this new bond here. That is the new bond that we've created using this blue arrow. Okay, so the arrow pushes are going to be our key or our map to figuring out what should go here. Sometimes we'll provide you the answer, and then it's up to you to just show us the arrows. But other times you'll see something like I just did, where we are presented with the reactants, and then we have to decide how they react, show it with arrows, and then show the final product, as I did here. Let's move on to the next pattern, and that is the loss of leaving group. And so we can use this reaction. And if we take a glance at this reaction first, we'll observe that the chlorine has basically become unattached from the carbon structure, and so the arrow is that's the only arrow we need for this loss of leaving group, and that arrow is showing the carbon-chlorine bond breaking, which is exactly what we see in our products. The loss of leaving group can also have 2 arrows. It's not limited to just 1 arrow. So if we have this set up here, we could get also loss of leaving group, and that will look like this. And again, you see we're breaking the C-Cl bond, and we are forming a double bond here between the C and the O. So this is 2 arrows. They're both considered loss of leaving group, and sometimes we might even write down the abbreviation for the pattern underneath the arrows just to make it more clear, or perhaps a quiz or exam question will ask us to label the arrow pushing pattern, and in that case this is what we're looking for, a label right below the equilibrium arrows here. The third pattern is proton transfer. Again, we abbreviate it PT. Here's one example. What we're going to do here is, let me draw in these lone pairs. Sometimes with arrow patterns, it's a lot easier for us if we draw in the lone pairs. And remember that a Lewis structure doesn't always require lone pairs, but as you saw in the nucleophilic attack, I used a lone pair in my arrow push. So here we can draw an arrow like this, which shows the lone pair attacking the hydrogen. Of course, hydrogen cannot accommodate two bonds, so we need to get rid of this existing bond, and that's going to form a new lone pair on the oxygen. And so if we draw the products then, and of course at first we won't expect you to be able to draw the products. We'll probably give you the products as a means of helping you decide how the arrows will proceed, but I can draw the products here. There's my new lone pair, there's the original lone pair, and so now I've protonated an aldehyde. That's how we would describe this in English words. I just protonated the aldehyde. And so we see that this H is the proton that is transferred. We can label it PT underneath the equilibrium arrows. And also you'll see that there are two arrows here. A proton transfer will always require two or more arrows, unlike loss of leaving group and nucleophilic attack, which potentially could involve only one arrow. So here is another example of proton transfer. We might start with a protonated ketone. You'll see I'm drawing in lone pairs here because I know that they're going to be necessary for this reaction, or at least necessary for me to show how the reaction proceeds. Okay, so here we have the sort of opposite occurrence. Here we take water, we're grabbing the proton, the extra proton from this ketone, and producing the second lone pair. So here's the first lone pair, and then this OH bond produces the second lone pair. So this is another example of a proton transfer, and of course it has two arrows as well. The lone pair from the water grabbing the hydrogen, so the water is acting as a base in this case, and then the protonated ketone is acting as the acid. It is giving up the hydrogen and reclaiming that OH bond as in the form of a lone pair. And then the final arrow pushing pattern is cation rearrangements. Sometimes we just call it rearrangement. And so that comes into play when we remember that if we look at our cations here, we know that the methyl cation is much less stable than the ethyl, or a primary cation, is much less stable than a secondary cation. There's a secondary cation, which is less stable than a tertiary cation. And of course that comes from the CH bonds sort of being used by the ion to donate electron density into the positive charge, into the empty p orbital. And of course over here with a tertiary, we have a lot more CH bonds than we did with a secondary, right? There's only 6 of them here. And then we have a lot more CH bonds with a secondary compared to a primary. So the whole idea with cation rearrangement typically is that we will form a secondary cation at some point during the mechanism, and we're going to rearrange that into a tertiary cation. If your mechanism ever shows primary cation formation, that's a good indication that you're most likely incorrect, that you've made an error somewhere, and you need to rethink your mechanism. So if you ever form a primary cation, you might want to rethink how you got there, and see if you can form a secondary cation instead. So there's two types of rearrangement. And again, I'm going to abbreviate it with RE. Let's look at this secondary cation. And it's, of course, very good to be able to quickly classify this as a secondary cation. And we observe this carbon next to it, which has the potential to be a tertiary cation. Of course, there's a hydrogen there right now, so it is not charged. But if this hydrogen were to move, taking its CH bond with it and populating or filling in that empty p orbital, we would end up with a situation that looks like this. The hydrogen left with its CH bond. This is called a hydride shift. And it left behind a tertiary cation. So we've made a more stable cation. This is a very favorable process. A similar event might take place if there is, say, an R group there. So again, this this carbon, the dot, has the potential to be a tertiary cation because it has a number of bonds to it. If we can take the R group with its electrons, this is called an alkyl shift, we leave behind a tertiary cation. And oftentimes we see that it's a methyl that's moving, so we might call it a methyl shift, but you can call it alkyl because R does not need to be methyl. R could be any carbon group, and it shifts along with the CH bond, and it again produces this tertiary cation. So we're going from secondary to tertiary, and that's going to be the most likely scenario for this cation rearrangement. We will not form primary cations very much, and if we form a tertiary cation, it's not going to rearrange because it's already in that low energy state.